NMR analysis of the chair-to-chair ring flip of bis-cyclopentadienyl titanium pentasulfide. In this video, we'll analyze our temperature-dependent NMR data to determine the activation energy and delta G, delta H, and delta S for the transition state of the ring flip. Here's our NMR in the department. And you can see this is the main unit. It's got the magnet and it's cooled with liquid nitrogen, and there's liquid helium in there as well. And then over here we have our center where everything is controlled by the computer, and we have some gases that are also supplied to the NMR. Really the only thing that's done here is to fill cryogens and put the sample in, and everything else is controlled by the computer. And there are many steps necessary to collect NMR data. Rather than list all of them here, a Word document has been posted in Canvas in the ring flipping folder, in which our instrument tech Cindy has detailed the necessary steps to collect this data. Just a simple overview of proton NMR. When samples are put into the NMR, proton spins are aligned with the direction of the magnetic field produced by the magnet. If these protons are bombarded with sufficient energy, they flip to a spin that is opposed to the magnetic field. Then when they relax back to a spin aligned with the magnet, a signal is produced. The amount of energy needed to force a proton into a spin opposed to the direction of the magnetic field is dependent on how well the proton is shielded by electrons. So here's the NMR spectra that was collected for our compound at room temperature, and this is going to be a really slow rate of ring flipping. And so here we can see two distinct peaks, one for the hydrogens of the ring in the axial position, and the other one for the hydrogens represent the ring in the equatorial position. As temperature is increased, the rate of ring flipping increases. Here are the first two spectra collected in the experiment, one at room temperature with the natural line widths for the proton signals, and one at 60 degrees. The NMR signal widths begin to widen as temperature increases and the rate of ring flipping increases. This happens because the rate of ring flipping is becoming faster than the relaxation time of the NMR signal. Here are all of the spectra collected for this experiment. As temperature increases, line broadening increases until eventually one peak cannot be distinguished from the other. This is the point of coalescence. A good analogy would be observing a propeller at rest and being able to see all the individual blades, as opposed to the propeller spinning very rapidly where you could not see the individual blades, rather just an outline of the space that the blades are occupying. As it turns out, we can use this line broadening based on a function of the rate of ring flipping versus the relaxation time of the NMR to our advantage. Based on these factors, equations have been derived that allow for the determination of first-order rate constants for the ring flipping process at different temperatures. If you would like an explanation of how the equations were derived, a paper has been posted to Canvas. NMR determination of the rotational barrier in N,N-dimethylacetamide. There are two methods we'll be using for these determinations, a line broadening method and a min-max method. Before we look at the equations, let's look at the data collected for this experiment. You will be provided this data in an Excel file posted in the ring flipping folder. First off, remember we're going to have to convert all ppm values to frequency by multiplying them by 400. So this column here and this column here are going to have to be multiplied by 400 to convert to frequency. Our temperatures are all going to have to be converted to Kelvin. And for most of the experiment, we're not going to need both sets of data in here. Remember, before we hit coalescence, there were two peaks. And so that's listing a line width for both of those peaks, and we won't need both of them. We're just going to need the top values, so you can go along and virtually get rid of the second line for each of these temperatures. And right there. Okay, and we're not going to need these two values right here, so they could probably be eliminated as well. So this will simplify the data a little bit, and we're going to need 6 temperature versus K data points, and so those are going to come from this line here, this line here, this one, and this one for all below coalescence values, and then we're going to need a data point for at coalescence, and we're going to need a data point for after coalescence. So let's look at the line broadening method, and we're going to be using equations 1, 3, and 4 in the manual for this method. We want to make sure we know what these values are up here and be careful how we're applying them. So the delta frequency naught is for the room temperature value, so we're going to need to know the difference between the frequency here and the frequency there, and that'll be used right here, and it'll also be used over here in this equation, equation 4. And then we also need to know what the line width is for the room temperature value, and that's delta frequency 1/2 naught. And that's going to be used right here and right here. And then for method 1, 2, we're also going to need to know what the line width is for each of those values below coalescence. So in other words, the ones at 60, 70, 80, and 90, we're going to need to know this value, and that's why we only need one of those 2 data points. We don't need to know both of these because theoretically they're the same. And so we need this value here, and it's going to be this value here, and then again this value here. So ultimately, for the line broadening method, we're going to have 6 K versus temperature data points. So let's move on to the min-max method, and this will be using equations 2, 3, and 4 in the manual. So I will note that equation 3 and equation 4 are the same for methods, both the line broadening method and the min-max method. But for all the temperatures below coalescence, now we're going to use this equation instead of this equation that we were using for the line broadening method. So here we're going to introduce this R value. So what is R? R is simply the intensity maximum divided by the intensity minimum. So if we go back to our data, we can see that for all temperatures below coalescence, we have an intensity max and an intensity min. We just take this one and divide it by this one, and that will give us our R value for each one of these temperatures below coalescence. And then this equation 3 will be common to both methods, and this equation here will be common to both methods. And so for the min-max method, we're also going to have 6 K versus temperature data points. So now that we've collected 6 data points, K versus temperature data points for each method, our line broadening method and our min-max method, we can apply those to equations to get our desired thermodynamic quantities. And the first equation we're going to be using is the Arrhenius equation. And so if we take our K values and convert those to ln K, and we take our temperatures in Kelvin and convert those to 1 over Kelvin, then we can plot those in a scatter plot, and you can see here that ln A would be the y-intercept, ln K is our y value, 1 over T is our x value, and so we end up with a negative energy of activation over R as the slope of the equation. So from this, it's apparent that negative energy of activation over R is the slope of the graph. Using this value, the energy of activation can be found by multiplying the slope by negative R. And remember, you'll be collecting data using both equations 1, 3, and 4, and also 2, 3, and 4. So you should have 2 graphs and 2 energy of activation values, 1 for each set of data. The Eyring equation will be used to determine the thermodynamic quantities of delta G, delta H, and delta S for the transition state of the ring flip, where Kb is the Boltzmann constant and H is Planck's constant. So in this case, ln K over T is going to be our Y value, and 1 over T is still going to be our X value. However, the Eyring equation cannot be used to directly calculate delta G. Delta G must be substituted with delta H and delta S in the equation. Once delta H and delta S are determined, these values can be used to determine delta G at 298 degrees Celsius. You're going to have 2 plots and 2 sets of values for delta G, delta H, and delta S, 1 for each method used. And in your report, make sure that you specify how the Eyring plot was used to determine delta G, delta H, and delta S. Requirements for pre-lab and report. The pre-lab assignment should include a statement of the purpose, goals of the experiment. An explanation of the system under study should be included. What you're planning to measure and how you will organize, manipulate the data you acquire to achieve the stated goals. So the equations that you're going to use for this analysis might want to be included there. It should also include the synthesis steps necessary to acquire the product. In your informal report, you're going to want to show how the Eyring plot can be used to yield values for delta H, delta G, and delta S at the transition state. I do just require an Excel spreadsheet for this lab, so whether you want to make a text box to include that within the Excel file or how you want to do that is up to you. But we do need that. You're going to want to prepare a complete table with all of the data, including all measured and calculated values and the data used to make your plots. So the data sheet that you're going to be supplied, that Excel file might be a good starting point for that. And just make sure all of your columns are well labeled to where I can see what calculations you've done. You're going to want to construct 2 Arrhenius plots and 2 Eyring plots, one set using the rate constants calculated from equations 1, 3, and 4, and one set using equations 2, 3, and 4. You're going to want to calculate energy of activation, delta H, delta G, and delta S for the transition state for both methods. You'll use 298 degrees Kelvin for the calculation of delta G. And you're going to want to compare your values to those in the literature. And I am going to be posting some literature papers that you'll be able to find those values. Since this is online, you don't need to attach a stack plot of your spectra to the report. It would be the one that we saw during the videos.